Complex periodic sounds are periodic sounds that have two or more frequencies in them. We can get complex periodic sounds when waves of different frequencies combine or interfere with each other. And there are many sounds in nature, such as phonation in speech, and the sounds produced by many musical instruments that are complex periodic sounds. A complex periodic sound will have an identifiable pattern of repetition. That pattern of repetition has a period, which means there is a frequency. In the case of complex periodic sounds, this frequency is called the fundamental frequency, also abbreviated F0. Here is an example of a complex periodic sound. It starts with a compression, but it doesn't have that sine wave shaped peak. It's got kind of a pointier peak, a little wobble, heads back down to near atmospheric pressure, the small trough and peak, and then down into a deeper trough that has another little wobble in it. So it's not a simple sine wave shape, but that pattern of overall up and down compression to rarefaction with that little blip in the middle is repeated over and over again across all of the different cycles. Complex periodic sounds can also be compared in terms of phase. So I have a solid and dotted version of this complex periodic sound with a small time shift between them that you can see if you compare the highest peaks, for example, or the lowest troughs, for example. That would be a phase difference between these otherwise identical sounds, such as when the sound is coming from the side, and these represent graphs of it hitting the left ear versus the right ear. If we go and look at that complex periodic sound, we can do the same sorts of measurements as we have done with simple periodic sounds. I will go back to my graph, mark my cycles, starting from time 0. I have another cycle in here, another cycle in here, another cycle, missed that pretty badly, another cycle right there. That would be 1, 2, 3 cycles in a time of 0.01. So that would give me a frequency of 3 divided by 0.01, which is 300 hertz. Peak to peak amplitude looks like the highest point is at 0.7. The lowest point is pretty close to minus 0.7. So we figure we have an amplitude of about 1.4 in peak to peak amplitude for this sound. Once we have the fundamental frequency, F0 of 300 hertz, we can figure out all the other aspects of this periodic sound just like a simple periodic sound, including the period of one cycle, the wavelength of this sound. So wavelength would be 38400 divided by 300. $34,400 divided by 300 is 115 centimeters. Okay, it's possible to compute the phase difference between these two curves, but when you get away from simple periodic sounds and its nice identifiable quarters of the cycle, you have to do a lot of extra math. That extra math is discussed on this slide. So, phase is the relative difference in timing of equivalent portions of two identical periodic sounds. If you want to compare those two sounds, doing what I did when I mentioned phase earlier, look at a high peak or a low trough as a reference point. We have to do two things. One is determine the duration of one single cycle. We can compute that since we know the frequency is 300 Hertz. The other thing we have to do is determine the difference in time between the two peaks or the two troughs or the two equivalent points of the two sounds. If I go back and do that for this sound, I made life a little easier on myself intentionally. From this trough, say, to this trough, I'm basically one of these tick marks on this axis. There are 10 of them here in 0.01. So that duration is going to be 0.001. Okay. Duration of one cycle is going to be computable from the frequency. 1 over that 300 Hertz is going to give me the period. That'll be something with some zeros and a bunch of threes, I think. 1 divided by 300 is, 0.00, and then lots of threes. 0.00, and as many threes as we feel like putting. The difference in time between the peaks of the two sounds, that's 0.001. Phase is the difference in time, 0.001 divided by the duration of a cycle, 0.00333 times 360 to turn it into units of degrees for phase, which is 0.001 divided by 0.00333 times 360 is 108. 108.1 degrees. Okay, so they're shifted by a little less than 1/3 of a complete cycle from one another. Again, relevant to localizing sound out there in the real world. Generally not something we're going to spend a lot of time with. Here is another example of a complex periodic sound. Identifying the periods on this sound. Starts here, a little above 0.3. That next equivalent spot is here, where there's a trough, a little peak, and a big peak. Trough, little peak, big peak. Next equivalent point is here. And here, whoops, and here, and here, and here. I have 2 cycles over a period of 0.01. 2 divided by 0.01 is 200 Hertz frequency. And then peak-to-peak amplitude is the distance from this highest peak down to this lowest trough. Lowest trough is around minus 0.5, maybe a little short of it. Highest peak is around 1, but definitely a little bit short of it. So 1.4 or 1.5 are both pretty good ballpark numbers for the peak-to-peak amplitude. When you're dealing with questions like this on a quiz or on the exam, there will be multiple choices, and I will not do mean things like have 1.4 or 1.5 as your two choices. Okay, I mentioned that we can create complex periodic sounds by combining simple periodic sounds together. This can be done mathematically by adding together the simple periodic sounds as they are described by their sine function. There will be a lab exercise doing this in lab number 2, where you can use prot to add two sine wave formula descriptions of a sound. And that's basically what I did here. I took a 300 Hz sound and a 500 Hz sound and added them together to get this complex periodic sound on the lower right, which starts at a peak, goes down to a trough, has a little wobble back up to a peak that's not quite as high, all the way down to a deep trough, back up to a peak that's not quite as high, another little wobble down to a trough that's not all the way down, and then finally all the way back up to a peak that happens at 0.01, and that is one complete cycle of this sound. Here are 4 examples of periodic sounds in both waveform displays and spectrum displays. The waveform display shows us changes in the sound over time in terms of the pressure, say on a microphone head. The spectrum display analyzes those changes over time to determine frequencies. So the first 2 sounds are simple periodic waveforms. They have the same frequency. You can line up their peaks and troughs with one another, but they have different amplitudes. When we look at them on the spectrum, since they're simple periodic sounds, they have just one frequency component. There's one bar there. Since that frequency is the same, that's located in the same spot on the x-axis. But since the amplitude is different, the first waveform at the top has a longer stick there, has a longer amplitude compared to the second one. The spectrum representation is really useful when looking at complex periodic waves like the lower 2 waveforms. We have a repeating pattern where there's like a peak with a wobble and then a trough with a wobble and then back up to that peak with a wobble starting again. On the lowest waveform we have a kind of a peak and then a wobbly down to a trough, back up to that peak and a wobbly down to the trough. So again, we have a repeating pattern. Determining exactly what those frequencies are from a waveform is impossible for all the frequencies other than the fundamental frequency. But the spectrum analysis can display all of those frequency components individually. So for the third sound down, we have 3 different frequency components, and for the 4th sound down at the bottom, there are 2 different frequency components of different amplitudes straightforwardly displayed on the spectrum. The way a spectrum figures out what these frequency components are uses something called Fourier's theorem, which comes from mathematics. It's basically a mathematical proof that you can take any complex periodic sound and break it down into a combination of simple periodic sounds, much like you can take light and break it down into different colors using a prism. Because of the math behind Fourier's theorem, if we take 2 simple periodic sounds and combine them together, the fundamental frequency of that combined sound is the greatest common factor of the frequencies, the biggest number that evenly divides into both of them. So for example, if I put a 300 and a 500 Hz sound together, I'm going to get a fundamental frequency of 100 Hz for that sound. 100 is the biggest number that will divide evenly into both 300 and 500. If I were to take a 300 hertz and a 550 hertz sound and combine them together, the fundamental frequency would only be 50 hertz, because the biggest number you can evenly divide into both of those, 300 and 550, is 50. But you are not really going to need to ever do this greatest common factor thing unless you go into speech technology, in which case Fourier's theorem and the math behind it will be important to you. Here we have a spectrum display of a complex periodic sound. I know this is a spectrum display because it's got frequency across the bottom and amplitude up the side. I know it's a complex periodic sound because there are multiple points, multiple sticks inside of this spectrum display showing multiple frequencies in it. In fact, this is a display of a sound that is very rich in component frequencies. It's a what's called a harmonic series that we'll talk about later in the class. It's actually a decent approximation of what the spectrum of phonation would look like if you could look at it without the rest of the person's head affecting the sound of phonation. When you make a spectrum analysis, say in the PROT program, you break sounds down mathematically by a well-known computer algorithm called a fast Fourier transform, or an FFT. That Fourier transform is applied over an interval of time. That interval is defined by the number of different points you analyze in the FFT. If you take a larger size interval, so you watch the sound over a greater period of time, you get a better frequency resolution, a more exact picture of what the frequencies in the sound are. If you take a smaller interval of time, you can watch frequencies change more easily because you're breaking the sound down into shorter durations of analysis. This is a parameter that we can play around with in the PROT program, and there are particular settings that we'll be interested in using to analyze particular types of speech. So here's an example of a Fourier transform creating a spectrum. The one on the left, which looks very, I don't know how to describe it, liney, it doesn't have a lot of detail, versus the one on the right, which has a much larger number of little peaks and troughs in it. The spectrum representation on the left is an analysis with fewer points. It gives us kind of a broader, a less precise, sometimes I joke and say it's a beer goggles version of looking at a speech sound. It gets all kind of smoothed out, whereas the one on the right has all the gory and nitty-gritty detail. That's an analysis over more points. Okay, so if we take a look at this spectrum representation and think about what sound it represents and also what kind of analysis was done, we see 4 very sharp points in this spectrum representation. Those look like component frequencies at 200, 500, 800, and 1100 hertz, all with an amplitude around 78, and this showing on the dB scale, which we will talk about a little bit later. Due to the sharpness of those points and also the amount of detail kind of underneath the overall outline of the curve, I would say this is an analysis that looked at quite a few points, many points, as opposed to few points. Okay, here we have another spectrum. It's, a little bit pointy, but not with nearly as much detail as the previous one. So in comparison, I would say this has fewer points. If you look at kind of the overall outline of the curve, there's some wobbling up and down that you want to mentally ignore a little bit. There are 2 component frequencies that very robustly stick out from that background. One is at 600 hertz and one is at 1200 hertz with amplitudes of about 55 at 600 hertz and 50 at 1200 hertz, something like that.